To recap the beginning of this unit that we've been dealing with electric charge and static electricity, we're going to quickly look through all the different events. So we have two charged particles. Like charges repel and unlike charges attract. Well, how do these charges come about? Well, we have a flow of electrons from one atom to another, and the uneven amount of electrons to protons is what gives us this positive negative charge. If you have more electrons and protons, the object is going to be negative. If you have more protons than electrons, then you're going to be positive. And these ideas we did pick up from chemistry when you learned about the structure of an atom. And so in our view of electric charge, we have the law of conservation of charge, which follows all the other basic laws of conservation that says you cannot create or destroy a charge or the movement of electrons. They have to be transferred in order for it to occur. They can't be lost just anywhere, and they can't create without being there already. And so how do we charge a particle is through a variety of ways. We can charge it through friction, and that's rubbing two particles of unlike materials together is really where we get this exchange of electrons from one object to the other. Or we can do it by induction, where we bring in a charged particle already into a neutral particle, and it causes it to organize because of opposite charges attracting, and all the excess charges want to leave that are not necessary. And so then we have this idea of polarization that allows these charges to organize themselves out, and anything extra flows out through another mechanism, which we call grounding. A grounding mechanism, whether it's your hand or a wire, allows any excess charges that are not matched up or pair up with their opposite to move on to another object. And when there isn't a break, if it's an even flow from one place to another, it's a very nice non-violent exchange. But if we have a jump between one particle to the other, that's where we have a violent exchange of charges, and we get static electricity, or hence a little bit of a lightning bolt, and that's what really causes lightning. The excess charges between one cloud to another, or between cloud to ground, after the organization of these particles, if they don't have enough of their opposite charge to match up with, they find somewhere to go find their partner, and hence we have this electric discharge. Now, along with electric charges, we have a certain area in which the charge affects its force. Like charges, we said repel, so they're pushing away. Remember, a force is a push or pull. And so they push things away if they're like charges. If they're opposite charges, they attract, so they come in closer. Now, a general rule is that negative charges attract, so they bring in towards the middle anything that's moving, and positive charges is a charge away from the center, so it's pushing things away. And because of this push and pull, when you have two positive to negatives, they attract each other because one of them's pulling towards it and the other one's pushing towards it, and so they combine. And we have a general area around the particle. So here I drew a negatively charged particle, just a circle with a negative sign on it, and we have a whole area around it that its charge is going to be affecting, or it's going to exert its force on objects around it. And so we have what we call an equation that we are able to calculate how big this electric field is, or how big the charge it can affect, by looking at the force applied, whatever the force is all the way around, and divided by the test charge. So if we have another particle out here that we know its charge, and we want to see how attracted it is or how much it's being pulled towards the center, we use this equation. E, the electric field, is equal to force measured in newtons divided by the test charge that's measured in coulombs. Coulombs is the name of the actual person who did the work on electric charge, and thus he named his unit. this particular charge after himself. Anyway, this whole charge around it is an area that is felt. Now, if you use magnets, you can actually also see a similarity between magnetic fields and electric fields, because a magnet can exert its force in a general area around it. It does not have to be touching, and it's the same here. But the further away you get, you start losing some of its force, and hence we can actually look at the field strength at which it can exert its power, if you will, over the objects around it. And so we can look at the equation. Electric field is equal to the Coulomb constant K for electricity times the charge that is exerting this field divided by the distance squared away from it. So if we have a point way out here, say here's a charge that I have, this time I used a positive, and I want to find out how strong my force is way out here in this spot, I would need to know the charge amount of this particle here and the distance between the spot that I want and where the actual charge is originating from. And by knowing this, I can calculate my K constant, which is 9 times 10 to the 9th Newton meter squared divided by Coulomb squared, multiplied by the fraction charge divided by distance squared. And this will give me the amount of force that can be exerted at this point way out here. Sometimes the further away that you get from the center spot, the less attraction you have, whether it's pulling attraction or pushing attraction, it starts to lose it. But these field lines will go out into infinity. It still will exert some sort of force way, way beyond its visible view of it. But same thing with the negatives, way beyond, it can still exert its force, but obviously the closer you get to that main area, the more of this force is going to be felt. Now, if we had two particles together and one of them's pushing, one of them's pulling a third object, then they kind of play this tug of war thing, and we could actually get into the vector quantities, because all of these are vectors. They all have a direction at which its force is applied. Negatives, the vector would be going in. Positives, the vector would be going out. But we could calculate it using the Pythagorean theorem and overall get the net charge of all of these together. But we're not going to get into that at this point of our unit. We're just going to be looking at the generality of the areas around it. Then we will be discussing what the charge is between two objects that are charged, and how we're going to see how, again, this area around it will affect the amount of strength that it will feel. And so we will be looking at the force exerted and between two objects in our next session.